USB stick is in the space where that one would go.
Okay, so sorry if I can't see you, but we'll do a little company overview here. We'll talk about the equipment, the process, the benefits of LiDAR, and the applications. So I started this about 4.5 years ago, like I said. Rob Noah is a good friend of mine who does the systems engineer. Blake Cagle happens to be a SolidWorks design engineer and also has a machine shop. So that's what kind of led us down the road of actually designing our own hardware and building around the system. Chet Green is in the energy industry, so he helps with the business relations. And Jeff Tyson is a 35-year retired banker and wanted to learn about LiDAR. And he'll tell you himself, he can barely turn the computer on, so this has been a big step for him. So, but he's doing a great job. So really the primary hardware components here is what we call the ELV16, the puck. It's attached to not only the M600, but we can move it here to the mobile mount. And then we built an access point to transfer that data from the LiDAR down to our interface and software. We use a GR5 for our base station. Anything 450 to 470 megahertz, Sokia, any of that, Leica, can be used. So our system's set up with the forward-facing GPS, which is your L1, your rear-facing is your L2, and then the sensor package and LiDAR camera sits below the M600. Right now, we're only integrated into the M600, but about any drone could be used. I mean, we can integrate in about anything. So some of the stuff that we've done is vibration dampening. Micro vibrations really were giving us fits in the early stages. So we found some specific IP67. They look simple, but for redundancy, they work really well with winds and turns and keeps the LiDAR pretty stationary. And a few customers had asked about safety. It's kind of going the extra mile here, so we added these right up here. These right here are kind of some safety in case 24 very sturdy bands decide to break. I don't think that's going to happen, but somebody wanted it, so we did it. And down here is where our hardware sits for the SD card, and it just slides on and off right there on the gimbal. So from the dampening right there on down is stuff that we put together and designed. So on the back you have your RTK link and then also your ground link, and you can just kind of get a shot. These just slide on and off, so they're very simplistic to apply to the system. It's got an internal battery of about 3 to 4 hours, so there's no recalibration or anything like that. So all the battery's internal, and if you can start and stop the puck with our system, so that can conserve your battery and make it. We've gotten about 6.5 hours out of it, so not having to recalibrate sometimes is really nice. You can use the Ethernet port, or we've put an SD card behind this battery compartment, so that's where all the data is stored in real time. You can just pop the SD card out, put it in your laptop, upload the data, and it's pretty quickly pull up a LAS file. So we've got actually 3 bin file settings, so it's pretty easy to transition. So this bin file setting is, of course, for scanning, I guess, forward, but collecting backwards. We have a bin file for it to go on the hood, and then also for the aerial setup. So we've really taken a lot of the input of calculations and numbers out of it. It's all preset. This access point here, you got a 900 megahertz Omni. You got the mobile antennas and the 2.4 gigahertz, so we can get through about any foliage. We really don't have any problems with link loss. And it does have an external battery, so it lasts about 8 hours. So right here you can see the 400 megahertz goes to the base station, 900 goes to the Omni, takes your data down to your laptop, and in real time you get to roll, pitch, and yaw, satellites, a lot of information feed from the LiDAR tube itself. So here's that interface. We've made it to where you can see how much battery you have left in the day, the current temperatures, again, RTK integer, where you want to be, satellites, L1 and L2 GLONASS, PAAS, and then it goes down through, and my engineer did this, and he doesn't want anybody to know where he lives, so that's why that's blurred out. And then your roll, pitch, and yaw. So the reason we have the antennas set where they are is to keep our yaw factor, 0.08, 0.1, keep that yaw factor down, and that's really how you're going to be able to tell if you're getting good data. So what is BoE Systems? We're really a software and hardware integrator. We've taken kind of that route. Right now, we're working with DJI. SPG is the IMU that we use, and right now we can do the puck or the HDL32. The Rigel, we have not, that's too big of a beast for us right now, so we haven't messed with that. And we're kind of a hybrid right now. I mean, we're doing services, quite a bit of it, until the market kind of shows itself to buying, and then also we lease our equipment as well. So we have training sessions and stuff like that people can go through if they want to get familiarized with the equipment before purchasing. So, LiDAR, light detection and ranging. So what we've done is really paired the GPS, the IMU, to get all that. You can get a 3D point cloud, georeferenced, to have a three-dimensional picture. You guys will probably hear a lot about all this today. Really the accuracy, the speed, the access to your data on site, safety of course, and we're trying to get to that affordable factor. The prices are coming down on cameras every day. IMUs are not moving as fast, but it's kind of the brains of the operation, so I mean, I think they're going to stay where they're at for a while. Applications are really endless. I mean, that's kind of what got me into this. Was I wanted something that was a niche, but also could cross many different aspects, industries. And to be honest, I didn't know a lot about LiDAR until 5 years ago. I'm completely honest. So I got into this and I was just amazed by it. And I could kind of see where the transition was going. And photogrammetry, of course, it's got its place, and I know there's a lot of good things for it, but we kind of took the next step thinking maybe eventually it'll get to the LiDAR stage. So I think Dan would agree that's kind of coming about now. So with some of the accuracies, I think Dan and I will, first of all, we're not surveyors. That's hurt us in some aspects. I go into engineering firms, civils. They said, well, what's your survey background? I said, I'm just a guy that happened to put some of this stuff together. So right out of the gate, I don't have Dan's background or anything like that, but we feel like we've learned a lot about this. I tell people you can't go and Google this stuff. You can't go on and figure out how to put the IMU and match that with the camera and the L1s, and also the software building. The design of that, luckily I know a guy, Rob, he's an MIT grad, knows a lot about data and how to move data. So the accuracy piece of this, so we use reflective triangles. That's how we pinpoint where our controls are at. They're designed with some paint that they use on the road, actually. The arrows you see is what we've actually developed into a triangle, and that's how we get reflectives down to where our control point is. So this is a broadcast projection, so when I talk about hitting control points, this is something we provide or our guys use in operations. So essentially here, if you look at 125 feet, so we shoot at a 40 degree, 140 degree. So we keep our angular airs down. So if you look at 125 foot, you're going to have a swath of about 297 feet. And of course, the further out to the side you get, the more angular air, we kind of consider that data obsolete. So we like to keep it the focal point right over the control point. So when you're planning your flights the way we do it, if we can get directly over that control, we like that where the best accuracy is. So this sheet really helps with operations when you have different terrain, understanding what your swath is going to be, because we like to keep our overlap at about 5 foot, if not less. So just guys in the post would probably like that quite a bit. So some of the differences, you guys have probably seen all the photos, from photos towards LiDAR. You can see here the power lines show up in the LiDAR, photogrammetry or pictures, kind of missing some of that. A lot of our data, we don't have to clean a lot of it. It's very crisp, the edges are refined. That's kind of built into some of the software we've done. so there's not a lot of cleanup. So that's just, here's some of the focus areas that we're hitting. Infrastructure's become a big one. A lot of dilapidated stuff out there. Once you start getting into this, you're kind of amazed by the amount of manhole covers I see in the middle of a creek. And it's like, well, they're like, that used to be in the land, but now it's receded. So there's a lot of uses for that. And some of the corridor mapping and utilities in this, one of the, you can just see here this is from 2016, I think, 15. You can kind of see where the ground based and airborne and UAV LiDAR is going, and the growth it's starting to happen through 2022. Here's a right-of-way or a utility that we did, just kind of showing the picture on the left, and that point cloud is just a small section, but this was shot at about 70 feet above the power line. So that's essentially how it just come out right there. No cleaning, we just converted it from what we call the BoE to LAS file, and then it's ready to go into post-processing. And, well, it's kind of funny, we eventually got to this was, what got me into this was the vegetation growth into a right-of-way. So then we eventually processed and actually showed some of these danger areas that can cross over the certain threshold. And so we marked that, and I said, well, it's pretty amazing we finally came around to that. I was glad to see it. And then we're just showing here, we showed point-to-point measurement. I've been told by civil engineers and people with utilities that they have algorithms for that. We're just simply showing you that we can measure a point-to-point and show you the terrain levels along that right-of-way. So some of the mobile LiDAR stuff is increasing. After we got the aerial aspect done, we're like, well, we could probably figure out how to do a mobile. So then we started designing it, and one thing you'll see on our mobile is the L1 and L2s are actually kind of faced back. Well, that's a custom design to where there's a 15-degree down and 15-degree up capture coming out of the puck. So we don't scan any of the L1s or L2s, so you can't just make a T out of it. We started doing that, it comes up in the captures. So we designed that and manufactured it, and so now you have a clear field of view to capture the data. And the mobile sector is increasing every day. Here's a mobile scan that we did. Customer wanted some classification, some topo features. So this was, I think it was a 20-mile project. So we labeled some of the end lines, some of the road markings, power lines, and then they're also using this for a fiber project. So they're boring their fiber lines, and they want to know where these features are at when they're doing this. So this drive, with the 16, it's about, you know how many points per square meter is about, 8 to 12 mile an hour. It's nothing, you're not flying around. I tell people this is a lot of like watching paint dry. It's pretty slow and go, but it captures a good point cloud, and the data is very relevant. So this goes on for a while, but you can see they wanted to know where the ditches were, things like that. So nice use case for that. And then sometimes what they'll do on an as-needed basis, we'll go in and we'll create a surface model for them if they want to know contours. Some equipment, when they take it down a slope, it can't go down a certain 45-degree slope, so we can give them that data. They don't send the wrong equipment out to the site. So this is just the classification we did. That's from that drive. They wanted to know where manhole covers were, trees, ditches. This is just a 10 model down here below, but we just took some of the classifications out of that. That's just a few of the things you can do with the LiDAR data. This was a 50-acre, for surveying, this was a 50-acre project. This was a surface model. We had to do 2 flights, almost, I think 2.5, 3 flights really. It was heavy foliage. We took all that foliage out. We sat down, the surveyor shot these ground controls, and then we of course put our reflectors on it and created this model for them. Right here you can see, so we have a different kind of methodology. I wouldn't say different, but this is how we do it. We have a black mesh that is put down, and then we have the control points that they shot, and then we take our reflectives and put it facing due north. So then when that drone's flying, that reflective will show you, and you can drill down in post-processing the closest to where that control is. That's how we find it with doing RTK. You can see here in control point 200 with that black mesh, there's no reflective. You can really see the triangle, and that's how we kind of drill down into that point. And that data is that's just a raw LAS file, so you can kind of see the puck does pretty well. And here's the output data. So what we're trying to do a lot of is really showcase what surveyors are doing, and then the output data that we're providing and the difference in the values. These are the difference in the vertical values. The reason 504, this is from that earlier picture on the 50 acres. It's 5.5 inches because the reflective was put on some grass, and so they should have put a rock on it and brought it down. And so it goes to show you how accurate this stuff can be. And since that happened, the reflective, that's pretty much, had a little bit of grass. So we should have pulled that grass or, made it to where it did get down to the ground. But for vertical accuracy, we were, I guess, I shouldn't say surprised, but we were happy with that. The average vertical, as you can see, is 0.06. So I think we were off 2 inches over 50 acres by the time we put everything together. So it was mainly for earthwork removal. So they wanted to know where they were starting. They started, taking all that aggregate out. And then so we calculated the volume for them. We showed how much more they had to go down, and they found it very useful. They were quite surprised, and they've been a good customer. So this is just a real quick video over Kansas River. It looks like it's a 1998 video, but I promise we did it recently. So this was over Kansas River. We took and scanned all this aggregate, and they removed all of this. So they wanted to know the volumes, and this was in last November. So we created our flight path, and there's our waypoints and how we flew it, and there's 4 controls that the surveyor shot. And this is just a fly through of a point cloud. It's colorized, and we flagged it with obviously the flags. And we're just showing the video up here to kind of show you how accurate the point cloud depicts what reality is. So what you'll see coming up here is the second control, and it's flagged right about there. And so it was pretty narrow flight, of course, but we're just kind of showing there that we're actually picking that up, and then I'll get to kind of move ahead here. But yeah, we just colorized that through Google Earth. We don't have an RGB or anything like that on our system yet. We always pick, and then there's the surveyor's shots. We should probably put that in an Excel sheet or something, but again, there's the output, and we were happy with those as well.
Okay, as quite like a fish guy, I want to know where on the Kansas River was
right
that?
off 435 by
Kansas City?
Yeah.
Okay.
Yeah, right, kind of over by Wedges.
Okay.
If you go by there again, it looks really nice. The construction,
It looks very
that
good.
all got cleared out, the river's flowing nicely. They did a great job with it, the construction company. And volumetrics, we've done a lot of that, just showcasing the volumes and kind of the clarity of the point cloud and the detail of what's going on. We've started doing a little more of this where there's vegetation on these volumes.
Mm-hmm.
So these guys want to get down through that grass and remove the vegetation. We can give them an accurate volume. These are just some 1-foot contours on a few jobs. This is actually a golf course. It was flooding a lot. It did not flood this last week, so the data provided these guys enough to where they could go in and expand the creek. Down below here is kind of a contour, but also these drainage lines here are showing you where the water's coming from. So that really helped them kind of understand this was the problematic area right here. And so the green didn't wash away this year. This is just showing you, this is in applied imagery, QTM. We kind of like that software. There's a lot of them out there, but you can kind of see how the flood model works. So follows the contour pretty close. And to kind of sum up, we've not done a lot of construction like this. We're just showing the footings. Some of the detail stuff can be brought out from the LiDAR, and then also the tin model. So that's what we do. And you can find us on Instagram, Facebook, Twitter, LinkedIn, or our website. That's what I got.